Consider the following example. Again, we are given this polynomial f of x equals x cubed minus 3x squared minus x plus 2, and we would like to find the roots of this polynomial, meaning the values, the x values, which will make this whole expression equal to 0. When we use a website like Wolfram Alpha and plug in this polynomial into that website, it gives us that the solutions should be those 3 values. So we are going to use Newton method to actually compute these roots, those 3 roots, iteratively by using the following recursive formula, which we proved in the previous video. And in this formula, obviously, we need f prime as well, so the derivative of our function, which we can easily calculate to be this. So the derivative of x cubed is 3x squared, the derivative of minus 3x squared is minus 6x, and the derivative of minus x is minus 1. The derivative of plus 2 is just 0, we can just ignore that term. So let's go ahead and apply the Newton method to actually find these 3 roots. So what we will do is I will start with, because it will be an iterative process here, I will have the following. So I will start with an old value. Along the way, I will plug in the value for f of x old actually, x old, and also f prime of x sub old. Oops, old. Actually, let's just make it upper script, yes, x old. And fine, let me also change this x over here, superscript, there you go, I mean uppercase. And finally, x sub new value of x. So in each step, so starting with an initial guess, I think in the example we solved in class, we started with 5. Let's have, I don't know, maybe 5 decimal place of accuracy. So let's change them into numbers. With 5 decimal places of accuracy. There you go. Actually 4, because look at that, 3.11. Yeah, so we need 4 decimal place. So let's just go ahead and change it. Okay, 4 decimal. I formatted the cell, so each number, anytime I write a number, let's say 2.5, you guys can see that it's formatting it to 4 decimal places of accuracy. So first things first, I need to calculate the value of x. So for that denominator expression, the value of x, the value of the function evaluated at that point, the starting point, which is in this example, this point. So it is plugging that point into this function. So it will be this point cubed minus 3 times that same point squared. And then minus that plus 2. So that's the function evaluated at that point, x equals 5. And if you remember from our previous video, that's the calculation that came out as well. All right, also we need to calculate f prime. So we need to value the function at the old point 5, but the derivative of our function. So the derivative, it's given here as well. So it is 3 times this squared minus 6 times that minus 1. So that would be the f prime. Let me make it lowercase here. There you go. And finally, x new will come out of this recursion. So it is just x old minus, so f prime of x old. So divide, okay, so let's maybe open a parenthesis. So f prime is this value, evaluated at the old point, divided by the value of the function, close the parentheses. And that's pretty much it. So, oops, I wasn't expecting that point. Let's see. Was that what we did calculate earlier? I think we calculated it as 4 points. Let me see, we got the correct. F prime divided by, oh, sorry, the other way around. Oh, the formula is wrong. It is really f of xi, so there's a typo here. It's f of xi divided by f prime of xi, so it should be the other way around. So it's really f of xi divided by f prime of xi. There you go. Okay, so this is the number that we found in our earlier calculation. So what we do next is, that point now is the old point in the next iteration of the formulas, and basically from there it's the same iteration. So for instance, what I will do is I will just copy these things, I'm just dragging it basically all the way. Oops, we don't need that. And let's drag that one all the way as well. So here is the number of iteration number. So iteration 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have all the way up to, for instance, 16 iterations. In fact, we realized that the answer was 3.1149, and we were able to get that result pretty quickly, actually, in 5 steps here. Do you guys see that? After 5 iterations here, that's the first time that we found that correct answer. Do you guys see that? So that's the root. Well, the third root in this case. So this thing is, maybe I can do it like this. There you go. This is the root, and afterwards it's all the same because it's getting even more sharp, right? So it's getting more and more accurate, the answer. So for instance, if I were to add more decimal place of accuracy here, let me just go ahead and do that. So you will see that the answer gets finer and finer, getting closer and closer to the actual correct answer. For instance, in just as quick as 2 steps, it doesn't even improve after that, right? So for instance, here it's already up to how many points? 1, 2, 3, 4, 5, 6 decimal places. It's correct up to so 0.00000001. So that's the error. The error is less than 1 in a million. Do you guys see that? Already after 5 iterations. After 6 iterations, 1 more iteration, or actually 2 more, 1 more iteration, we are good even up to 1 billion. So the error term is only 1 in 1 billion, less than that actually. So it's very, as you can see, the Newton method is very accurate. For a machine, this thing will just take milliseconds, right? Just 5 iterations. It's very easy. So how do we calculate the other 2 roots? So what we can do is, let me just go ahead and Control Z. Let's go back to what it was. Okay, there we go. Let's just take this. Well, actually, once we got the root, so maybe I can just delete this part. What I will do is the following. I will just carry this again, Control C, Control V. So, and then let me do it one more time, Control V. All right, there you go. And I don't need anything between them. All right, so we will just realize that instead of having the starting point as 5, for instance, what if the starting point was 0? Let's see what happens as a result. Do you guys see that? So we got this root. Actually, this time it didn't happen on the 5th iteration, but it happened on the 7th iteration. It took us longer than we needed, right? After 7 iterations, we were able to get to root 1. Do you guys see that? That's pretty neat. So this one happened in 7 iterations rather than 5. Let me just get rid of that. There you go. And the same way here, let's just get rid of this as well for the time being. All right, so let's see how many iterations is needed to get the remaining root. Because the remaining root is between them, so that I can start with, say, for instance, the point 1 or 2. That should give me the desired result. For instance, if I start with a 1, look at that. Only 2 iterations and done. Do you guys see that? In 2 iterations, I can get to the correct answer, 0.7459. So versus if I started at 2, 2 would have taken, wow, look at that. If we start at 2, we find the first root again. So 2 is not a good starting point for if you want to achieve the second root. How about 1.5? 1.5, that's a good solution, but it takes 3 steps. So for instance, let's use this one, I guess. So you might say, how do we know where to start the iterations from? It is it's just a guess basically. So you can just guess whatever number you want. Even if we started with the number 1 million, we would have gotten the correct answer, but it would have taken us much longer time probably, right? Let's take 1 million for instance, just a random number. If you press enter, oops, I need more space here. So let's see. There you go. Oh, there you go. So yeah, so the 1 million will take significantly more steps. Let's actually carry these further. Let's see how many steps until we get, wow, it takes significant, but ultimately it will hit one of the roots for sure. So let's just go all the way. After, wow, so you look at that. After how many iterations is that? After, yes, exactly. After 36 iterations, ultimately we captured one of the roots. So if instead of 1 million, we started out with minus 1 million again, or minus 1 billion, for instance, again, we will ultimately, 1, 2, 3, 1, 2, 3, ultimately we will reach one of the roots, but it will probably take a long time. So for instance, it took 36 steps to reach to the root, but in this one it take, wow, look at that. After 53 steps, we were able to reach to one of the roots. Isn't that nice? So in a sense, you will ultimately reach to the roots, but the thing is, because this is cubic, it should have at most 3 roots. You might want to try different values until you hit the desired root, right? So 1.5 hits it very neat in a very fast way, in a sense. So it's a pretty good deal. So this is the Newton method in evaluating, for instance, the roots of a function. But now you will see in the next video, I'm going to show you guys some applications of how you guys can use this method to evaluate some expressions as well. So it has a lot of wide applications in a sense. All right, so see you guys in our next lecture.